All right, so our next group is the team that works with the LA Dodgers over the summer, the reigning World Series champ, I should say, LA Dodgers, with our project partner, Sam Fleischer. So we have weapons of best production, predicting the optimal pitch arsenal adjustment for superior stuff plus. We have Gabriel Eze, Neha Kotha, and Danny Nolan. So Gabriel is a junior at Center College in Danville, Kentucky, double majoring in math and data science. He loves playing soccer and video games. He's from Nigeria, and he has quickly developed a love for algebraic equations and word problems, which sparked his interest in data science and analytics. And this passion drives him today as he's excited to continue exploring ways data can reveal truths and shape the future. Neha is a junior at UPitt, currently studying data science with a minor in CS and digital media certificate. She's actively involved in the Sports Analytics Club, Women's Computer Science Club, and Smart Women's Securities. Also, she's currently working as a stadium event and operation intern at Steelers Stadium, which work with Pitt and Steelers home games. She's aspired to work in sports analytics or sports media analytics in the world in the future. And finally, Danny is a senior at Bucknell University, majoring in statistics and minoring in economics and classics. On campus, Danny has worked for the math department for parts of the 3 years, both as a research assistant and a course grader. Also captain of Bucknell's ultimate frisbee team and is an avid Phillies sports fan. And he hopes to work in sports analytics after earning his undergraduate degree. So, guys, please take it away.
All right. Thanks so much, everyone, for being here. Before we get into it, huge thank you to Dr. Ron Yurko, Kwong Win, and the entire CMU Sports Analytics program for giving us the opportunity to do this. I had a blast this summer. And then another thank you to Dr. Sam Fleischer with the Los Angeles Dodgers, our external advisor, who just gave us a lot of support and guidance, helping us get from point A to point B, finishing up this project. So yeah, I'm Danny Nolan.
Gabriel.
And I'm Neha Kotha, and today we'll be presenting to you Weapons of Best Production, predicting the optimal pitch arsenal adjustment for superior stuff plus. So, baseball pitchers are constantly looking for new ways to improve their performance and keep the opposing batter off balance. And one way that a pitcher will achieve this is by creating adjustments to their pitching arsenal, which is the types of pitches that a pitcher will throw and the attributes of those pitches. And now a baseball pitcher will change their arsenal from season to season. And because of this, our main research question throughout the summer was, can we create a pitch recommendation system that suggests with conviction which pitch a player should add and how effective it might be? So this graph here is just showing one of our earlier exploratory data analysis plots, and it was just a way for us to kind of guide our research early on. And it's depicting the number of pitchers who added or subtracted a certain type of pitch from between the 2022 and 2023 season. Now, each box or facet is representing a different pitch type. And again, this was kind of a way for us to see the trends in the league of what pitches are added and subtracted to an arsenal. And now for our data, our research consisted of data from the 2021, 2022, and 2023 MLB seasons. And we chose to just focus our attention on these three because of inconsistencies in previous seasons. And at the time of our research, the 2024 season was still ongoing. And we used the Baseball R package to scrape the majority of our pitch data from Fangraphs. And then our release point and spin rate data came from Baseball Savant or StatCast. And then some notable data cleaning that we did is create a 5% usage cutoff rate, meaning that if a pitcher did not throw a pitch more than 5% of the time, we eliminated that data just to avoid any type of misclassifications. For example, a pitcher might only throw a pitch once or twice, or even by accident. So something like that might skew the results of our modeling, so we eliminated those. Additionally, we filtered to only include pitchers who threw over 250 pitches throughout a season. And then we to account for left and right-handedness, we scaled horizontal movement, since different-handed pitchers will generate movement in opposite directions. And then one of our most important values here throughout our research is what's called Stuff Plus. And Stuff Plus accounts for only the physical traits of a pitch, and the attributes that we focused on are velocity, horizontal and vertical movement, spin rate, and release point.
Okay, so before we get into modeling and predicting, we first need to discern whether Stuff Plus is actually a useful predictor for performance. So here we have a simple scatter plot, with each point representing a pitcher and a season. And on the x-axis, we've got overall Stuff Plus. On the y-axis, we've got K9 plus. K9 is just strikeouts per 9 innings. And then the plus simply scales it, so 100 is considered league average. Anything above 100 is considered above average. Anything below 100, below average. And then you could say that if a pitcher had a K9 plus of 130, his strikeouts per 9 innings would be 30% better than the average pitcher. And then we have that each point is colored by xFIP minus. So FIP, which we've mentioned earlier today, stands for fielding independent pitching. And it is a similar stat to ERA, and it attempts to remove any impact the defense has on performance, on runs allowed. So same scale as ERA if you're thinking about it in that way. The X just stands for expected, and then the minus again, scaling. So 100 is league average. Anything below 100 this time is considered better than average. Anything above 100 is considered below average. So just looking at the scatter plot here and the trends within it, we can see that an increase in overall Stuff Plus is associated with both an increase in K9 plus and a decrease in xFIP minus, which again is good. So we're just able to take away here that Stuff Plus is in fact a useful predictor for performance, and it's worth trying to predict in the future.
Modeling approach, we applied on all fronts a pitcher's physical characteristics to predict the optimal performance of a separate pitch variation that a pitcher might be seeking to add to his arsenal. And so we discussed and explored multiple modeling strategies and finally came around to the option that is dependent on relationship between, pairs of pitches. However, recent discovery of the 2-HGBR added a dynamic approach to our research, which we'll get to later. And so we began by closely analyzing unique pairs of pitches with similar horizontal break and vertical break, and started out with using the fastball to predict sinker Stuff Plus, as fastball is the most commonly thrown pitch in the MLB and in the minor leagues. Now, two main modeling choices. We had the lasso regression and random foresting regression. The lasso regression aims to find a sparse solution by throwing out predictor variables that are insignificant, whilst introducing a penalty term called lambda that increases as these coefficients shrink towards zero. It really attempts to create a very linear additive model that doesn't place any emphasis on possible relationships between explanatory variables. Whereas the random foresting regression takes a multitude of bagged decision trees, averages them in the hopes of accounting for interactions between these predictor variables. On every iteration, this is done by taking only a random subset of the data, and this is a means to project independence from one tree to the next. And an additional benefit of the random foresting regression is that it prevents overfitting of the data. So the chart to your right is one of the cases of our model comparison, where we have the lasso and the random foresting regression on the horizontal axis, and we have our average RMSE of the fastball traits predicting sinker and Stuff Plus on the vertical axis. Now, RMSE just stands for root mean squared error, and it's just a simple calculated value that shows how far you are from the actual Stuff Plus. And the point on the chart are gotten through a 5-fold cross-validation where our training set data is evaluated continuously against the test set data. And just observing the graph, we can see that both the models do better than the intercept-only model. But then again, almost always the random foresting model beats the lasso regression in terms of having a lower RMSE, which is what you want to have.
All right, so which model is the winner? So this visual here summarizes the results of each model's performance relative to the response pitch variable, which is shown on the x-axis. And each individual point is representing the RMSE value of a different pairing of pitches. So for example, let's say you look to the very bottom right-hand point that's in blue, and that's representing the RMSE value of a fastball predicting the response pitch of a splitter. And you can see by looking at all the response pitches that generally the random forest is the lowest RMSE value for each response pitch. It beats out the intercept-only model and generally clears the lasso model. And the superiority of the random foresting, what that tells us is that the interactions that occur within the predictor pitches are significant in predicting the results of the response pitch, which in this case will be the stuff plus value.
Yeah, so as Neha had said before, we're taking the pairing, your pairing of pitches that yields the smallest RMSE, and we can build predictions for each pitch. And then in an ideal world, players can use these predictions to add an above average pitch to their arsenal, just as a way to improve performance from year to year. So we can take a look at two real life examples. First one, I'll just do that, yeah, it works. Ryan Presley, who was 2021 through 2023, he was the Astros closer. A really good pitcher, but our model suggested that he would have had a great changeup in 2021 and 2022. And then in 2023, he decided to add one, and it had a stuff plus of 136, which was among the best in baseball. Imagine how much better he would have been if he had added that in 2021 or 2022 instead of waiting until 2023.
And then another interesting story that our research also revealed is about Nabil Crismat, who is a pitcher for the San Diego Padres. Now, in 2021 and 2022, his fastball suggested that he would have a pretty poor slider if he had chosen to throw those pitches during those seasons. And interestingly enough, he actually added a slider to his arsenal in the 2023 season, and it came out to have a stuff plus value of 69, which is well below the average league slider, which is actually at 110. So again, if you look here to this chart, this is our predictions using the fastball traits to predict the stuff plus of a slider, and he's actually the #1 bottom stuff plus value. And one thing that could be notable to mention is he now plays for the Padre minor league.
So just some conclusions from the work that we did over the summer. We were able to construct relatively reliable predictions for stuff plus, and that the teams can use those predictions throughout the regular season and into the playoffs to try and gain a competitive advantage over their other teams. We're able to discover which pitches are most useful for predicting others. So interestingly enough, changeup and curveball were paired very tightly together, while cutter and splitter were paired in one sense, but then splitter and fastball were paired in another sense. And then we were able to indicate through the random forest model important interactions between pitch traits through that selection process. And then some limitations of our work. First of all, we had some inconsistencies between the Fangraphs data and the Baseball Savant data. They classify pitches in different ways. So Fangraphs doesn't have a category for a sweeper, while StatCast does. So trying to navigate that discrepancy results in some inconsistency, and we're lumping pitches together, and they shouldn't be lumped together. Another limitation is that stuff plus cannot be the only thing that goes into success. Location, pitch sequencing also are very important in success, unless you're like Tommy Kahnle and throw 61 straight changeups in the playoffs. I don't know how that worked, but it did. And then finally, our predictions over the summer, they don't take into account a pitcher's whole arsenal. So it would be unfair to assume that it's only one pitch that we can use to try and project the effectiveness of another. You would think that all of them kind of have some net effect. And that's what we tried to do like going on after the summer.
So yeah, as we alluded to earlier, our modeling strategy was largely based on relationships that occur between pairs of pitches over the course of the recent fall semester, we were able to address this limitation where our predictive models do not take into account the whole arsenal. And so this is done using the methodology called histogram-based gradient boosting regression tree. And it's a tree-based Python regression too that has an inbuilt native support for handling missing values. This is good because most of our data is sourced publicly, so just due to human error, there's a very high chance that there is a lot of missing data cells, which there is in our data. And yeah, one advantage of this is that it does allow us to, include every pitch type in any given player arsenal, and then it can spit out a numeric value, which we can also scale similarly to way the random foresting model and Lasso does it, so that the average is 100 and anything better than that is advantageous, or anything less than that is disadvantageous. But one disadvantage is that it doesn't fare better than the random foresting model. As you can see, the blue dot always is the first one on the plots, but the HGBR model does, provide quite a bit of competition to the Lasso regression model. So yeah, future work would try to fix discrepancies between pitch type classification between Baseball Savant and Fangraphs. We'd also like to explore how a pitch responds to the integration of advanced metrics like runs above average or wins above replacement or runs expectancy wins, which otherwise is called runs exchange for wins, etc. And also adjust for other variables excluding your raw quantifiable pitch metrics, such as the trajectory of the ball, along its flight path, and also even possibly the overall permutations that can occur within any player's given arsenal and how they are trying to sequence their pitch in series. And yeah, thank you.
We also have a Shiny app here where you can input different pitchers as well as pitch types. So please scan that and take a look.
All right, great job. Thank you. Okay. All right. That's the first time I saw that histogram gradient boosted trees imputation. Interesting. All right. I'll turn it over to Kwong to introduce the next batch of students. Hopefully you scanned the QR code. I purposely was pausing here.